we are exploring on the dimensionality side of things. What is curse of dimensionality? What are the techniques to reduce that? Then we will dive into PCA and SPD into more deep, and then finally we would have our Python implementations. Okay. So first of all, what is the meaning of dimensionality? In a data set, you can have any number of variables. You can have 10, 20, 30, 50, 500 variables in a data set. Why would you have so many variables? Just imagine that you are working for let's say a telecom subscriber, telecom organization, and you have your subscriber number. That is nothing but the mobile number, right? You had the mobile number of the customer or the subscriber, and after that you can have many different usages. Like, first of all, let's talk about the demographics ones, right? You could have gender, age, income. Yes, I understand not all of them will be completely filled, but you could have such variables, right? Then you could have variables such as the usages, right? So the SMS, data, voice. Now again, voice can be further divided into whether it is a within a state, like local or international, right? Something like that, right? Similarly, for voice, you they would have different call charges, right? The duration will be different. Okay, okay. The whether it is night time or daytime, that will be different, right? Then there can be other variables like whether it is on the weekend or over the weekdays, right? So basically, all these variables, they are helping you to analyze the data better. And similarly for data also, right? For the data that it is it a 1 GB pack or 2 GB pack. What is the usage? What is the usage more on the weekdays, on the weekends, days versus nights? All those things will come into picture. Similarly for the SMS. Okay. Then comes your transactional values. Like for example, whether you are a prepaid customer or a postpaid customer. If you are a prepaid customer, how do you generally recharge? What are the denominations you use? 10, 15, 20, 100, what are the denominations you use? Do you recharge from a retailer? Do you recharge in online mode? So all those factors will come into picture, and based on that, again, multiple derived variables can be created, like average transaction value or average recharge value, right? That can be one of the variable. Okay. Similarly, how many days you are on network, right? In a month, out of 30 days, how many days you are on the network? That's again one of the variables, right? That is called VLR in telecom lingo, visitor location register. So the point is that based on such a rich data set, your number of variables can be very high, right? And because of that, your complexity of the solution will increase. So look here, if you have only one dimension, you can easily represent your data like this. If you have two dimensions, you would need more data points to represent your data. If you have three dimensions, your complexity will increase. So that is precisely the curse of dimensionality. That means you have so many variables that it is difficult for you to shortlist the customers, to shortlist the product, whatever is the analysis you are doing. That becomes very cumbersome, very time consuming, and very complex. And as you can see on the graph on the right hand side, your performance of classification algorithms, it also decreases after you have reached an optimum number of variables. Okay, like for example, if you have 500 variables in your data set, it will be very difficult to analyze that. Okay, now to so that is called the curse of dimensionality. Now you do have a lot of methods to reduce the curse of dimensionality. First few which I will discuss are quite manual. Like for example, if you have sales, if you have number of invoices, you can simply divide sales by number of invoices and you would get average transaction value. What is the average spent by the customer? So that is one way where you are combining two variables into one. Good. Then other one method can be that you simply remove variables, and perhaps that is the most simple method, right? Simplest of all, simply drop view variables which you think are not good. Like for example, let's say in the same telecom example, if I have data on customers shoe size, hypothetically, taking a very stupid example, but let's say you have data on customers shoe size. Now for telecom, it will not matter what is the customer's shoe size, right? So you can drop that variable. But obviously in real life, you will not get such variables. So in that case, simply dropping would require a great depth of domain knowledge. So dropping will not be as easy. Then second one can be the one which I just now discussed, that you can simply combine few variables. So I'll just note it over there. So you can drop the variables, you can combine the variables, right? You can try to find out what is the correlation between the variables, right? So and then you would say that, okay, these two variables are correlated with each other, so let me drop one of them. Okay, that is also one of the method. Like for example, if you have for a business, you have number of customers versus revenue. So we would think that yes, the higher the number of customers, the higher will be the revenue. So it can be one of the method, but again, not a completely scientific method, not a very complete, very scientific KPI based method, you can say, right? So that is why we do have algorithms based method, like you can see PCA, NMF, LDA, GDA. So there are multiple other methods. I'll give you a list of them, and you can explore them. So PCA is one, principal component analysis. Then you have SVD, singular value decomposition. Now singular value decomposition and SVD, many times they are SVD is called as a different version of PCA, but we are treating them as separate. Yeah. Then you have LDA, linear discriminant analysis. You have GDA, you have that is generalized discriminant analysis. Then you have non-negative matrix factorization, right? That is called NMF, right? Then you have MDS, that is multi-dimensional scaling. There is one more, isomaps. There is TSNE, right? There is autoencoders. There are multiple methods for dimensionality reduction. Now, you would think that what is the purpose of having such a huge number of dimensionality reduction methods? The reason is that not all the methods might be good enough for all types of problems. Okay, based on the complexity in the dataset we have, we need a higher degree of more complex algorithm. Okay, and again, these dimensionality reduction methods, they are not limited to text to structured data. It can be used for unstructured data too, right? And we do have deep learning based algorithms, deep learning based dimensionality reduction algorithms too. Okay, today we are going to discuss PCA and SVD, right? Now, what is PCA? First of all, PCA is principal component analysis. Now let's take a step back from here. What do we want to achieve? I told you that, let's say if you have 500 variables, so not all those variables are important. Not all the variables are significant. So what is important? How do I know that? What is the next step for me? Out of those 500 variables, if I choose, let's say, 80 variables, 80, which are the most significant one for me, which are most important for the data set. So in that case, I still can solve the business problem. Now I use the word important. Important is a very subjective word. How would you define that a variable is important or not? Right? How would you conclude that a variable is significant for that problem or not? So what happens is we try to measure the variance explained in the data set by those selected variables. So what it means is that if I have a data set, right, and let me draw the data set. So I have a data set. Come on. Yeah. And this is my data, right? And based on this data, if I can create, if I can, convert this data or represent the same data using lesser number of variables, at the same time capturing the maximum randomness or the variance in the dataset, I have done my job. So if the original dataset, it was using 500 variables, and let's say using 80 variables, if I'm able to capture 95% variance in the dataset, it is good enough for me. That is the logic, right? So over here, so what happens in PCA is, in PCA, you have your principal components. So you can see that you have first principal component over here, and you have second principal component perpendicular to it. Okay, so what is happening in the background? In the background, I am trying to fit an equation first, right? So I fit an equation first. This can be equation, this can be the equation for the first principal component, whatever, right? Remember the linear regression method that we used? So, okay, so I found out, let's say, that this particular equation, this one, which I am again making, it's this one, it is able to justify its logic. That means it is able to reduce or minimize the error. So I would call this equation, because this is the line of best fit, as my first principal component. So I would find that, okay, this is my line of best fit. So it might be able to explain, let's say, 40% variation in the data set. First principal component, 40%. Okay. Then I will take another principal component which will be perpendicular to this one. Why perpendicular? Because if I say take in the same direction, the variance captured will not be high or high enough. That is why we take second principal component which is perpendicular to the first one. Okay, fair enough. So we took the second principal component, and let's say second principal component, it is able to capture obviously less than 40, because if had it been more than 40, it would have become the first component, right? So it will be less than 40, and let's say it is 35. So with the help of two principal components, I have explained more than 75% or 75% variation in my data set. So let me take third principal component. Third principal component, again perpendicular to this guy, to these two. This is my third principal component. Okay, my third principal component, it is explaining, let's say, 25%. My fourth principal component is explaining, let's say, 15%. Okay, so let's say make it even less. Let's say 15% over here and 10% over here, right? So you can see that it will be hypothetical case 12 and 7. Yeah. So you can see that using 4 principal components, I'm able to explain 94% variation in my data set. Right? Now that is a very good reduction I have done in my number of variables required. Okay. But at the same time, what is the meaning of this principal component? So what happens is, if you look again, we have used equations. Now those equations are nothing but they are a combination of other variables. Like over here, over here, if I have such variables, I would create derived variable or new variable from there. That means the derived variables, they can be the combination of, let's say gender, age, and income. So I would create a variable which can be like A times income, right, minus, let's say, whatever, B times age, something like that. Okay, they will be the new derived variables. So these variables, as you would think that yes, these variables are good enough to explain the variance in the data set. So in PCA, the process is that you start with normalizing your data as a first step. Okay, so that means it ensures that your variables have, all of them, they have the common representation. Why that is important? Because it is the possibility that your weight is in tons, your price is in rupees, right? And in that case, your weight will be like 1.1, 1.12, 1.15, right? Whereas the other dimension, it is increasing in thousands. That is why you have to first normalize your data. Then you would get the covariance in this normalized data sets. Then, I'll note it, covariance. Then you would calculate the eigenvalues and eigenvectors, right? Eigenvalues or eigenvectors are nothing but a representation or transformation of data set. Like for example, if you stretch something, right, without changing its basic nature, then you sort these eigenvalues in descending order. Okay, in descending order, and you simply select the eigenvectors which are able to give the maximum eigenvalues. Now, there can be a question that how do I calculate these eigenvectors and eigenvalues, and do I have to do everything from scratch? No. Our libraries, they are good enough to um to create these eigenvalues, create these eigenvectors for us. Okay. But in PCA, there is a problem. The problem is that the new variables which are created, yes, they can explain the variation, but the original variables, that do not exist. They are lost. That means if you want to do some, you want to have some business logic, like for example, call duration. Call duration is a very important variable, as you would think. But using PCA, the original call duration variable will be lost because it would be transformed like this, right? It would be transformed somewhere like this variable. So your original call duration variable has been lost. And since it has been lost, you cannot derive any business insight from that. Like for example, you would have said that customers whose call duration is more than 100 minutes in a day, they are more profitable, they are more they stay with us for a long time. They don't leave us, they are loyalists, they don't leave our network. So if you're so in that case, this insight based on PCA you cannot derive because your original variables have been lost. Okay. because it is a combination of different variables. And that is why the new variables that are created, they do not share the original column name. Okay, but yes, one thing is for sure, that the newly created variables, they are lesser than the original number of variables. Okay, now then comes your SVD. So PCA are the original combination of is the combination of original variables. In the context of SVD, singular value decomposition, it is based on the concept of eigenvalue decomposition. So what happens over here is, I'll just put to full screen mode. On the screen, on the right hand side, if you look at that. So if you have an original matrix n cross m, right, and you decompose your matrix like this: n cross n, which is the eigenvector, m cross n, which is the singular values. Singular value means that bearing the the diagonals, all of the values are 0. Okay, and then you have the eigen vector matrix, or it is also called the covariance matrix. Okay, so if you can decompose your matrix like this, okay, so you can use SVD on top of that. Okay, so SVD is nothing but a different, you can say that a different form of PCA, right? But one thing is for sure, that these first matrix and the second matrix, they are symmetrical with each other. Okay. In a nutshell, if you have to remember this, SVD can be said as an enhancement of PCA using eigenvalue decomposition. Okay, SVD is an enhancement of PCA using eigenvalue decomposition. Okay, so PCA, it was the linear transformation of input variables using principal components. All those components of linear transformation, choosing the best component, etc., they remain the same. The major process, the major steps, they remain the same. The only difference is that in SVD, we use a different approach. We use the eigenvalue decomposition. It has been replaced by the singular vectors and singular values. Okay, the eigenvalue decomposition, it has been replaced by singular vectors and singular values. Now what are these? What are these singular vector and single values? These ones, the one that you can see over here, they are symmetric and square matrices. Their eigenvalues are either positive or 0. I mean, that is quite a complex mathematical concept to be explained in the session. But that being said, what I would like to simplify it further, I would say that SVD, or singular value decomposition, is an extension of PCA, wherein you are using singular vectors and singular values, right? If you want to explore more on that for singular values and singular vectors, I have explained that in the book in detail, because we are short of time, we have to go to the code also, right? So what I will, just to keep it at a very simple level, SVD, it uses singular vectors and singular values instead of PCA, where we had a different approach, but it can be called as an extension or enhancement of PCA. Now coming to PCA, So let's say you have this data set, right? So this is the singular cyclic decomposition. You have your data set over here, right? You import your PCA from here. You have your iris data set, that is the standard data set that we have used over here. This is the head. I saw the first 5 lines. Describe, that means what is the mean, standard deviation, minimum, maximum, all of that. Shape, how many row columns I have. The variables I have over here, my x variables, that is my target variable, and my y variable, that is my, sorry, x variable, that is my independent variable, and y variable, that is my target variable. So over here, standard scaler, it allows me to scale my data set. Okay. And then I calculated, then I use the fit transform method to transform my data set. Then I'm calculating my covariance matrix over here. And from that, I can calculate my eigenvalues and eigenvectors. Okay. So in using NumPy, I can calculate my eigenvalues and eigenvectors. And this is how eigenvalues can be arranged in the descending order. This is to show the eigenvalues, the calculation of eigenvalues and eigenvectors. But let's say if I want to use PCA as a method for that, what should I do? So again, from this imported library, I can invoke a variable PCA. I can invoke, this method PCA, and I have to simply feed my transformed data set. Transformed data set is nothing but my scaled data set, right? So I fit my transformed data set using PCA, and then I want to see that what is the explained variance ratio by my fitted model. Explained variance means nothing but how much variance has been explained by the principal components. Okay, so over here we got 4 components. The first component is able to explain 72% variance. You can see that. Let me zoom in. You can see it over here. The first component is able to explain 72% variance. The second component is able to explain 23% variance. Then 3.6% and 0.05%. So if I plot these variables in a chart, you can see that first component 72%. So let's say if I take only the first 2 principal components, I would still capture more than 95%, 95.77% or 95.8% to be precise. I will be able to capture using the first 2 principal components, more than 95% variance, right? I understand the original data set, it had only 4 variables, and from 4 to 3, it won't look that, okay, you're reducing from 4 to 2, but still just imagine it's a toy data set. So over here we are reducing from 4 to 2. Imagine that if it's a big data set and you are able to half it, right? So using 2 variables, we are able to explain 95% variation. This is the plot. If I want to simply plot on a cumulative scale, that number of principal components, 1, 2, 3, 4, if I have how my explained variance, how it moves. So obviously for the first principal component, it was quite high, immediately a jump, and after that it it tapered after second principal component, and that is expected also, right? You would not expect your principal components to explain all the variance in the data set. Okay, so I used 2 principal components, so now I can give that okay, I want to use 2 principal components. I don't want to use 3, because 2 is still able to capture 95% variance, and I'm able to reduce my variables. Good. So I used 2 principal components over here, and based on that, I want to explore my data set over here. So you can see that, we created one more variable, species, and species data set, it has been replaced. And then I can create my plot over here, right? If I want to use four principal components, then how will my data will look here? Because using four principal components, the entire data set, I will be able to capture almost all the variance in my data set, right? So that won't be of much use, because instead of having four components, in that case I would use the four original variables. What is the logic, right? That is why in this problem, for this particular problem statement, we would use two components. Now if I go to another data set, okay, so over here we have a banknote authentication data set, right? And we would explore that how can you use that how can you use PCA to improve the solution. So we have our regular libraries, our matplotlib, numpy, pandas, cbon, etc., etc., to do the analysis, do the visualization, all of that. And then I have my cbon plot, which has been used to analyze the distribution. Okay, so using cbon plot, I can analyze the variance, skewness, kurtosis, entropy in the dataset. And then I have the pairwise plot over here. You can see that for each and every variable, I can look at the relationships between, sorry, I can see the relationships between each other. Okay, that's good. Then I have my target variables and my independent variables. So those are created. Okay, train test split is done in this step. Okay, so we have taken a random sample of so the train test split is 80-20, right? There is a component called random state, which generally question that what is the meaning of this random state. Random state means that if you want to replicate the same results again, right? If you want to do the same steps again, you would get the same split of the training and testing over here. So I have my random split over there. Then I have my standard scale over here, right? Then I generate the covariance matrix and the eigenvalues for the PCA. Okay, covariance matrix and eigenvalues, they are created over here. And then I want to check the cumulative variance, which is being explained. So you can see that for the first one, 54% variance is being explained. Second one is explaining cumulatively. It will be 86% cumulatively. So the second one is exploring close to 31% of the variance, right? That is why it is cumulatively 86%, right? Third one to 95%, 95.4%, for 95.5%, right? And that's how it continues. So I can explain increasingly cumulatively higher variance using my different principal components. Okay, so over here we have sorted the eigenpairs, the same eigenpairs using PCA. Okay, now if you want to reduce, okay, let's explore one thing, that if you fit your data set with PCA and without PCA. So this is my original data set, right? And after PCA, what is my accuracy? What are my measurements? My KPIs. So before PCA, my data set was giving me 98% of training accuracy. After PCA, it has given me 77% of training accuracy. Before PCA, naive Bayes, right? It has given me 84% of accuracy. After PCA, it has given me 74% of accuracy. Now, why, despite that, we are saying that so over here PCA has not improved the accuracy. But that being said, it is true over here because the number of variables are not very high. They are not like 500 variables in the dataset. That's one. The second point is that the overfitting has reduced. In the training dataset, it was giving me 98%. On the testing dataset, it has given me 84%. So the model was clearly overfitting. But post PCA, the model is not overfitting. Okay. So that being said, uh, PCA, it allows you to reduce the dimensions, right? If the number of dimensions are quite high, and if the number of dimensions are like 500 or 300, then our regular naive-based methods or KNN or logistic regression, they might not be able to handle that because it will be a very highly dimensional dataset, very complex to handle. Over there, our dimensionality reduction techniques, they will be of very help, right? This entire thing there, it has been checked in over here, in this repository. So you can simply, take this repository. I am pasting it over here.